growth of legs. When the gene misfired, flies grew legs in the wrong place, on their heads in place of antennae. In normal flies, legs grow from the midsection, the area called the thorax. So Levine and McGinnis decided to hunt for the gene in the thorax of a normal embryo.
The expectation is that antennapedia would be active, expressed in the thorax, the developing thorax of the embryo. But who knew?
Levine and McGinnis had to do something no one had ever done before. They had to find a way to see a gene in action.
We wanted to light up the gene, and it was very painstaking work.
The project called for new and untested methods.
At first, it didn't work very well, and there were a number of technical problems to solve.
The team had to find a delicate balance of radioactive probes and toxic enzymes. Too much of either would destroy the embryos.
The process was not very gratifying on a day-by-day basis. Unbelievably tedious.
It took months of trial and error.
People often said, you know, you should try something else. You know, this is too long shot. You know, you're just wasting your time. But we kept going.
Finally, late one night, all the work paid off.
And there was this moment when we saw that the gene was turned on in a band in the middle of a very early embryo. This had never been seen before.
The antennapedia gene was acting like a master switch, turning on the segment of the embryo that would become the thorax. The implications were mind-boggling. If single genes like antennapedia could define whole segments of an animal, these genes were acting like architects of the body. And if one of these genes turned on in the wrong place, striking changes to the body could result. It seemed that Levine and McGinnis had uncovered the genes responsible for the evolution of bodies. But there were still doubts. The work had all been done in fruit flies. What about other animals? Did they use the same mechanism to build their bodies? An answer would come from Switzerland. In 1994, Walter Gehring of the University of Basel isolated the gene that triggered the growth of eyes in fruit flies. The gene was called eyeless because flies without it developed with no eyes. Gehring knew of a gene in mice that worked in the same way. He wondered, were the two genes the same?
And this question we tested by taking the mouse gene and putting it into fruit flies to see whether flies can understand the message of the mouse.
Gehring replaced a fly's gene for eyes with the mouse gene.
And to everybody's surprise, the mouse gene works perfectly well and can induce a compound eye in the fruit fly.
The fruit fly grew normal fruit fly eyes using a gene from a mouse. Not only did the two creatures use the same mechanism, they used the same gene. This was the mechanism behind extra wings, legs sprouting from heads, and Bateson's deformed animals. The century-long search was complete. The genetic engine of the body's evolution turned out to be a tiny handful of powerful genes.
So what this means is in some ways, some sense, evolution is a simpler process than we first thought. When you think about all of the diversity of forms out there, we first believed that this would involve all sorts of novel creations, starting from scratch, again and again and again. We now understand that no, that evolution works with packets of information and uses them in new and different ways and new and different combinations without necessarily having to invent anything fundamentally new, but new combinations.
Suddenly, the commonality of form among animals was understood. Animals resembled each other because they all used the same set of genes to build their bodies. A set of genes inherited from a common ancestor that lived long ago.
And what we see now among all the animals are just variations on a body plan that existed 500 million years ago.
And there's only one inescapable conclusion you can draw from that, which is if all of these branches have these genes, then you have to go to the base of that, which is the last common ancestor of all animals, and you deduce it must have had these genes. So the whole radiation of animals, the whole spring of animal diversity has been fed by essentially the same set of genes.
Ed Lewis shared the Nobel Prize in 1995 for the discovery of the universal set of genes that builds the bodies of animals.
And so, yes, it came as a huge surprise, not only to people like my mother, who says, my God, an earthworm and a mouse, an earthworm and me, share things in common, but it came as a surprise to other scientists that there was this profound conservation of mechanism of building embryos among all these different kinds of animals.
What about us? Our bodies are built from the same genes that build all other animals. Yet, we are different. No other animal designs or creates like we do. We seem so special. It's hard not to think that we're somehow an exception to evolution. But of course, we're not. The transformation that led to us was no different from other transformations. Our crucial turning point seems to have occurred when our ancestors left the trees and began to walk on two legs.
We don't know exactly when or even where our ancestors became upright and bipedal. We think it goes back well over 4 million years when these ancestors came out of the trees and began to exploit food sources on the ground in terrestrial habitats. One of the key elements that would have been so useful to them would have been freeing their forelimbs, their hands, to be able to gather and carry foodstuffs over long distances. Once that happened, it opened up an extraordinary breadth of possibilities and opportunities.
Most bipedal hominids went extinct. But one branch went on to evolve larger brains. That branch eventually led to modern humans. So how did this crucial transition to two-legged walking begin? Liza Shapiro of the University of Texas looks for clues in living primates.
When you look at the fossil record, all you have really is a pile of bones. It's a non-moving entity. There's not much you can know about it unless you look for living analogs. So if you look at living animals, you've got the bones, but you can also look at how they're moving.
In their movements, living lemurs resemble tree-dwelling primates that lived up to 50 million years ago. We didn't evolve from lemurs, but they may be the best living analog for those distant ancestors.
When we're trying to reconstruct a scenario about how humans evolved bipedally from this ancestor, we have to know what it was we started from if we're going to come up with an explanation for not only how we made that transition, but why.
Today, Shapiro is gathering data on the movement style of a lemur